Excellent. Right, so the next talk we've got is Bill Geyer giving us a helicopter update. And Bill, are you about ready to go?
I am.
Okay,
Can
go
you?
ahead.
All right. All right. I'll go ahead and share my screen and share my video.
Thanks, Bill.
Oh, in a second. There you go. There is me.
Yep.
Is my screen sharing?
No, I haven't got screen sharing yet. We've
Oh,
just got the video.
okay. Share screen. All right. There we go. And now I'll go ahead and launch it. Does everything look good?
Looks great.
All right. Well, good evening. As I was introduced, my name is Bill Geyer, and I'm here to give you the helicopter update and a little bit of background on myself. Joined the ArduPilot community as the maintainer about 2 years ago, maybe a little bit over 2 years ago. Uh, I'm an aerospace engineer. Have about 28 years in flight test as a flight test engineer, and currently I'm also teaching helicopter stability and control as far as academics. So well, for my talk, I wanted to go ahead and just introduce a little bit about rotor dynamics to kind of set the stage for some of the other things that I'm going to be discussing during my talk. Then I'll go into the current state of our trad heli code, discussing some of the things there. And then I have a kind of a laundry list of current projects you can see there as far as different things that you can see they're all kind of oriented towards the control for helicopters, the tuning, the command model, that kind of stuff, and some of the things that Leonard had alluded to in his talk as well. And then I'll go through and talk a little bit about what my future work is going to be. All right, so just to start off with a kind of bring everybody up to the same playing field from a rotor dynamics standpoint. We talk about the rotor blade has 4 degrees of freedom. And real quickly, just kind of walk through those. We talk about the first one being the rotational degree of freedom, which is essentially the rotor system rotating about the shaft of the helicopter. And we, just a note there is that we are constant rotor speed vehicles. Then you can talk about the flapping degree of freedom. So we talk about a plane of rotation as being a plane that is perpendicular to the shaft. And so out of plane motion, or vertical motion, as I might say there, is what we call our flapping motion of the blades. And that can be done through a flexible beam or a hinge, various ways to provide for that flapping degree of freedom. And this is essentially how we create moments to control the aircraft. Then there's the lead lag degree of freedom, which is this in-plane motion. So it's this, I call it the horizontal motion there, but it's in the plane of rotation. And so this really is a nuisance mode, right? We require this degree of freedom only because the blades are flapping. And it kind of, you can think of it as that, hey, when the blade flaps up, the CG of that blade gets closer to the center of rotation. And kind of like an ice skater effect, when the ice skater pulls their arms in, they speed up, and so that's the same thing that's happening here. Same idea, conservation of angular momentum. So as the blades flap up, they get closer to the center of rotation and they speed up. So you either have to plan to restrain this lead lag, or you have to allow the lead lag motion. And so again, it's kind of this nuisance mode. And generally, this mode is also has low damping, because it's just the drag of the blade that's all really creating that the damping for that mode. And then lastly, we can talk about the feathering degree of freedom, which is essentially the blade pitch. And that's basically what the pilot is controlling through the Swashplate. Matt Kier gave a great explanation on the Swashplate and how it lifts and vertically and lowers to provide collective control, and how it tilts forward and aft, left and right, and that provides for this once per revolution cyclic blade pitch, which we'll talk a little bit about more here. So different types of rotor systems. They have you have your teetering, articulated, and the one you showed previously was an articulated rotor system. This is teetering. Its definition there is that we have this flapping hinge over the shaft. And so kind of the difference between full scale and model scale helicopters, most full scale helicopters don't have any type of restraint. And when I say restraint, like some of them some of them do have like springs in there. Um, to provide a little bit of a moment on the shaft, but most of them do not have any type of spring. Essentially, they have um, flap stops, which are generally used just to when the blades are slowing down, but they generally do not want to hit the flap stops when they're flying. It's a bad thing to happen. But with model scale helicopters, they have put in these like hard rubber dampeners, what they call hard rubber dampeners. And there's one shown right here. And so here's the pin for the axle for the to provide the teetering over the shaft, and then this hard rubber dampener kind of sits inside the head, and that's what provides more of a moment onto the shaft, right? Because if you didn't have that hard dampener and it just teetered, you really can't put any moment on the shaft. But then again, and also for the lead lag degree of freedom, in pretty much in all RC helicopters, it's pinned, where with a teetering rotor system from full-scale helicopters, generally they'll restrain it and basically beef up the rotor system to withstand those loads. Oops. Here's kind of a hingeless, what I'll call a hingeless, more or less hingeless in flap, and a flap degree of freedom. And so basically this is a Century multi-blade rotor system, and they have, it's mainly aluminum in the shaft here, and then there's plastic grips. But basically, this aluminum here really isn't that flexible. More or less where you're seeing the flexibility and the flapping is coming from the blade, and this kind of the inboard portion of the blade is really where the flapping is occurring there, because these they're very stiff. And again, the idea behind putting these dampeners on the teetering rotor system and making more of like a rigid hub here is to provide really fast response on the aircraft, because there's moments that are being transmitted directly into the rotor shaft. All right, so a little discussion on rotor phase lag, right? And this gets into flapping. So um, rotor phase lag is this change in the azimuth angle from when you hit the max cyclic pitch to when you see the max flapping. So you can see here, max blade, we're just basically saying, hey, let's do a aft longitudinal cyclic. And for you fixed wing guys, this is an elevator input, right? And so, so aft longitudinal cyclic, basically you see that this rotor's rotating, and it matters on the direction which the rotor is rotating, right? So if it's rotating counterclockwise, the blade on the left side is hitting max blade pitch at right abeam the shaft, right? And then on the right side, it's seeing mid blade pitch. And so basically, the phase lag for a teetering rotor with no dampener is 90 degrees, right? So 90 degrees later, steady state flapping that'll occur is going to be basically pure longitudinal flapping. And why we want this is because when we tilt that tip path plane, that creates either the thrust vector is displaced from the CG, which creates a moment there. And if we have some sort of flexible structure, or a flapping hinges, that kind of thing, dampeners, that'll create direct moments because of this tip path plane tilt on the shaft, and creates that very responsive aircraft. Now, now that I said that, right, there's a little gotcha here. So, like I said, for a teetering rotor system with no dampeners, you'll see pure longitudinal response from the blades and flapping 90 degrees later. But now, when we have these dampeners in there to kind of stiffen up the rotor system, we have offset where the flap hinge is no longer over the shaft. It's actually set out apart from the shaft. That'll create kind of more stiffness in the system. And so now we see this less than 90-degree blade flapping or rotor phase lag. And what does this cause? Well, it causes coupling. And what you'll notice with helicopters is that they are a coupling mess. They, it's pitch and rolls coupled for RC helicopters, even for full-scaled helicopters that have these other, and most of them don't have teetering rotor systems. Typically, most of them have, offset or some sort of blade flexing, flex beams that provide some sort of stiffness to the rotor system. And so it just creates a lot of coupling between the pitch and roll, and then also there's coupling in the collective to yaw. So yeah, we're not only a vibrating mess, but we're a coupling mess as well. So that's some of the things we have to fight and deal with when we're controlling helicopters, unlike with multicopters where you're fairly uncoupled in all of your axes. All right, so that was enough of the little lesson there. And now we'll talk a little bit about the state of the code. I came on, like I said, about 1.5 years ago, somewhere around there. I came on as a co-maintainer with Chris Olson, and it was great working with Chris. We really got a lot accomplished over the 2 years that we worked together, maybe 1.5 years, 2 years. First thing we started diving into is kind of maintenance type stuff. I worked with Tridge on the servo library, getting that up to speed, kind of bringing the code, the trad heli portion of the code up to speed with the rest of it, because Leonard and Randy had kind of forged ahead with this spool logic, and they kind of just put the little snippets of code inside the trad heli just to make things happy. But basically, they said, hey, now that you're in here, do some work, get the spool logic up to date. So that was a big advancement, bringing the spool logic up to bringing trad heli up to speed with spool logic, and that went into 4.0. So a lot of the improvements, enhancements. So Rob was the previous trad heli maintainer, did a great job in trying to bring the code up to, making it useful for our helicopter enthusiasts. But some things fell to the wayside after he had left the program, and so we had to kind of made a few more improvements to what he had done already. So great work that he had done. So the first one was this 5-point spline throttle curve, right? So this basically, so when a helicopter is not, so for like electric helis, it's kind of, most of the time it's pretty easy because they have internal governors, so that helps maintain constant rotor speed. But for internal combustion engine helicopters, they require to have a throttle curve. And basically this is essentially adjusting the throttle output based on collective. And you can see a little plot over here showing the different throttle curve points. And so you have collective request down here, which comes, so this in the RC world, this comes from the pilot and his transmitter. But in our world, basically this comes from the ArduPilot, ArduCopter internally. So it takes the pilot's request as far as collective and turns it into the collective that's going to go out to the rotor, and then hands that off to figure out what the servo output's going to be for the throttle. And the reason why we do need this throttle curve for internal combustion engine helicopters is so that it helps the users can adjust this so they can maintain a fairly constant head speed throughout their flight envelope. So that was a big first forge ahead there. Chris and I had worked together to do some wiki updates. I'd recently worked to do wiki updates. Chris did some setup videos, which were really helpful for users. And then more recently, which I'll talk about here on my next slide, as far as this heli setup page, we had done some changes with that. There's a laundry list, and I'm going to go through some of these things in detail on my next slides. Last one here is this autonomous auto rotation, which Matt Keir talked about this morning. Awesome work, and really great to see that first part of it made into the CITL. I'm looking forward to future work with that. So here's the new, I call it universal helicopter setup page. And this is kind of a, came off of what Chris had done with QGC and wanted to kind of port that into Mission Planner. So we had a consistent setup page between both both platforms. And big thanks to Michael Oborn for helping get this into Mission Planner and really bringing us to be very consistent across platforms so that we can, so it doesn't confuse our users. So next we got the rotor speed governor. Another huge step forward for the helicopter community to have this governor. So like I said, internal combustion engines could use a throttle curve, and that kind of kept, they had to tune it fairly well to keep a consistent throttle or consistent head speed, but this rotor governor kind of took it a step further. You know, before they had to use external rotor governors that they bought out, you know, outsourced rotor governors, but now we have this internal rotor speed governor. This is solely built by Chris, and he had worked with Ferruccio, and those guys have worked together, and really great piece of work. It's based on, Chris did a lot of work and looking at mechanical governors, and basically made it pretty much strictly a proportional controller. He had played with some integral PI controllers, but they just was a lot of lag. So, and got into some surging, and he found that this proportional controller based off of mechanical governor was really spot on. And so it uses a throttle curve as kind of a feed forward input. And also in case of an RPM failure, RPM sensor failure, it would be able to fall back on the throttle curve for the pilot to be able to bring it back and land. But you can see over here on the right in this plot, sorry, it's a little bit of an eye chart, but you can see initially he does engages the governor, and this spike here is basically the governor bringing the rotor speed up on to the 1500 RPM, and then throughout the this you know, he does some punch outs here, and you can see that the rotor governor really holds rotor speed very well within probably 20 RPM of the desired rotor speed. Again, requires an RPM sensor, but that's fairly cheap, and for the huge capability it provides, and definitely overwhelming response from the users on the governor performance. They really loved it. I'd worked with Chris because I wanted to always do a Swashplate library, wanted to have the ability for users to kind of select the Swashplate rather than, you know, before we had this, you know, you could enter the azimuths, kind of call it a generic Swashplate, but you know, now we have this capability where the user can specify any of these Swashplates up here. H1 is just kind of the mechanical mixing that's done between the pitch, roll, and collective. They call it an H1. So that's all mechanical. So all you're really specifying is collective, pitch, and elevator and aileron. Whereas these other ones are basically forms of CCPM, collective cyclic pitch mixing. So so you can do these as well as reversals of these if they're turned backwards all through the code now with this Swashplate library. And we even brought into the mix four Swashplate or 4 servo Swashplates, which is a big improvement to help some of the users in the community. So the big thing about the Swashplate library also is it helped the dual heli users, right? Before they could only specify one Swashplate type that was applied to both heads, and with this Swashplate library, it allows them to basically put separate Swashplates on each of the heads and configure them differently if they want. The other thing is I retained the generic H3 because I like this idea of this phase parameter. Remember we talked about how the rotor phase lag from when it achieves maximum cyclic maximum flight flapping from when it saw maximum cyclic input. Well, if it's not 90 degrees and you can't manually adjust it on your Swashplate, you can electronically adjust it through this parameter called this phase parameter. And that's what kind of was a nice feature, I thought. I kept it in there in a generic. I'm almost tempted to kind of push it back into all the Swashplate types that you can adjust this electronically, because there is such a huge mixing going on there, that if you can at least or coupling going on, if you can at least pull off that control coupling and kind of reduce that, you still have disturbance coupling, coupling that occurs because of disturbances, but you know, at least you've taken one thing out of the mix, and that's your control. So that was a nice thing that I thought to retain. My other thing that I liked that I did with the Swashplate library is kind of doing this linearized servo output. So the Swashplate essentially is controlled by 3 separate servos. And so depending on where they are in the arc of the arm, most of the time, if you're up at a high collective, your servo is going to be up in this region, this upper region here. And so basically, if it's not linearized, if that motion isn't linear, then you're going to get even coupling due to the fact that the servos aren't moving properly in coordination with each other. So this linearized servo output basically modifies this servo arm throw to remove the nonlinear movement because of that arc. So basically, you can see here, if you're requesting a 0.5 output on the servo, if 50 degrees was 1, right, then 0.5 from an angle standpoint is going to be 25 degrees, which is, I can't see this. I'm going to have to minimize this guy here. Get rid of that. Okay, so which is basically 0.423, but that's not half of 0.766, which is the linear movement for this 50 degrees. So what I did is I back calculate the angle that's required to get the halfway point, or that proportion for the linear movement. And then you can see here it's now 22.5 degrees really to get the half, you know, half that linear motion of the full 1.0 there. So had that tested by Eris at Velos Rotors, which was great. He thought it was a great addition, and it reduces the 4-servo Swashplate. There's a lot of binding that can occur in 4-servo Swashplates, and so that helped a lot with that. Virtual flybar. This is designed to help with this acro mode. A lot of users, I know Chris flies acro a lot. I do not touch acro too much, but those that do fly acro felt that that the you know, it's a rate command system, so you move the stick and you get rate output, but when you center the stick, you want it to hold attitude, and that's kind of the design of the controller. Well, with helicopters and trying to make fine movements and precise movements flying it manually in this mode, they find it to be very robotic type feel. That it's just too stiff in the feel of the aircraft. And so it's so that was a problem. And they also felt that when you're on the deck and you're trying to you know, you're sitting on the deck, unlike multi-rotors where your propellers just stop, with helicopters, we will sit on deck, we'll sit on the ground and turn rotors for 2-3 minutes. I mean, you could sit there for an hour if you want, if you have the fuel, but basically you're going to start the rotors, you're going to keep them running until you're ready to take off. And so that could be some time. And so with the way the code is done for acro, if you move your cyclic, if you move that pitch or roll stick, right, elevator or aileron, you could see that it's going to command the ghost is no longer, the ghost is released, you know, the target it's going to seek that new target attitude. And so that becomes a real issue because they just don't know while they're trying to lift off where that target attitude is, or even while they're on the deck. So that was a real issue. So this virtual flybar is there to provide the short-term attitude retention, kind of like a real flybar helicopter. I guess I didn't explain what flybar is. So flybars are before we had 3-axis gyros, and the flybar essentially is a gyroscope essentially, and it helps stabilize helicopters. Most of the time with full scale, they have just basically weights at the end of a bar that provides kind of a gyroscope to stabilize. It gives like rate damping as well as some short-term attitude retention. But the but with a flybar, it also has these paddles that essentially help with also providing a little bit of control, reducing control loads. In any case, this simulates that. I know Leonard, when I first talked to Leonard about this, he was like, what do you mean you're going to leak off attitude? He's like, it should be following attitude exactly. So this really shouldn't work if you really tuned your helicopter well. And so it really, and what I've discovered now is it's the fact that there's such a if you look at what I'll show later, is there's such a delay in helicopters achieving that attitude that this kind of comes naturally, that you're always going to be delayed so that you can leak off attitude. And so it provides a little softer feel to the aircraft, and also provides a little more safety on deck, and a little easier to handle the aircraft when it's on the ground. Because if you do displace the stick and get the target attitude off of what the aircraft is actually at while it's on the deck, right? The ground's resisting its ability to roll, but if you push it too far, we still have enough moment generating capability that we could actually roll the aircraft over on the ground. So what this does, if you center the stick, it'll actually just leak that attitude off and return the aircraft kind of back to the target of the zero attitude. So we found that to be really nice. And there's kind of how you would set it there down at the bottom, last point. All right, so tuning challenges. And this kind of leads into my my current work. Some of the things that I've found in working with the code and tuning my helicopters is that we have these really lightly damped rotor modes. And because of that, it makes it really difficult to increase your proportional, the P or D gains in the rate controller. So that becomes a real challenge because you have to rely on other things to provide stabilization as well as um, disturbance rejection. One of the other things is, we had a lot of these vibrations coming through that, would mess with the effectiveness of the feedback loops, because you saw that your signal was really had a lot of noise in it, and so you had to reduce your low pass filters down to some really low cutoff frequencies, which then now adds lag to the system. So that was a real one of the things that I felt was a challenge. And again, now, not only are the low pass filters providing lag, but there's also lags due to the aircraft response in nature, right? So the rotor response, right? I said that, hey, there's some phase lag between when the rotor sees that max cyclic to when it achieves the max flapping response, and that's kind of a steady state thing. There's still 1, 2 to 3 rotor revolutions depending on the aircraft, but 2 to 3 rotor revolutions before it actually achieves that steady state of that tilt back. So there's that time. That's around 50 to 70 milliseconds is this time constant for the rotor response. And you can see there's probably longer lags if you have a softer rotor system. But also there's these additional lags for things like actuator lag. Oh, wait a second, Josh, that's right. He doesn't have any actuator lag. He always likes to boast about that. But you do have these actuator lags that you could see. And in my helicopters, which I have slower, I don't have UAV CAN servos, but I have these traditional digital servos, but which are pretty fast. But you still see some lag in the response of the actuator, and that's kind of this up to 20 to 50 milliseconds of lag. And the last part that I was talking about challenges is this target response and kind of how it's unrealistic for larger, slower aircraft. It's requiring way too much for these aircraft. And I know we can detune the the target response, but still there's some discontinuities that, and I'll talk about more of that later in that response. We'll go over that. All right, so let's talk about the rotor dynamics and kind of what the rotor modes are. So we have these lightly damped rotor modes that, like I said, limit this P and D gain tuning. You know, I said that these, you can really drive the rotor unstable. And so let's step back and talk, you know, here's vibrations versus feedback instabilities. Vibrations are from, you know, the rotor, you know, it has vibrations at typically the 1 per rev or at the rotor, actual rotor speed, and then multiples of the rotor speed. Those are vibrations. Users have a lot of trouble understanding kind of when I'm talking about vibrations versus feedback instabilities. And so, you know, here we're talking about feedback instabilities, and that's mainly due to this, these two modes in the rotor. One is the flap regressive, and the other one is the lead lag regressive. And so these are specific frequencies in the on the rotor. And so with the flap regressive, that seems to be the one you hit most often, the first one you hit when you're tuning the P gain. And so it's around 3 to 5 hertz. In the roll axis, it's probably 5 hertz. In the pitch axis, it's around 3 hertz. And that really, that frequency depends on the axis and its inertia as to what the frequency is. And then it also depends on how stiff your rotor system is. I had my 4-bladed system I had on an Airbus X3 or Eurocopter X3 style helicopter that I had made homegrown. And that one had, you know, the rotor frequency, the flap and pitch frequencies were up around 5 hertz. And so I was actually able to actually notch that frequency and be able to drive my P gain up to something that I could actually fly the aircraft just on P gain alone. So that was pretty interesting, but that's the only one I've been able to do that with. All these other helicopters that I've experienced and tried to help folks tune, this 3 hertz in the pitch axis tends to kill you. You just can't get away from that, and it really affects the dynamics of the helicopter. The lead lag regressive, like I said before, this is attributed, or maybe I didn't say, this motion is attributed most to your we call ground resonance. So if you've heard of helicopters that get into ground resonance, it's because of this lead lag motion. And so this occurs around 50% of the rotor speed. And so you'll definitely, you could definitely excite this as well with these P, mainly I think it's like the D gain that tends to excite that. So these are the modes that we basically have to fight and try to tune against and be able to try to stay away from those without exciting them. So here's a plot of some Bode plot here, but let me go over the stuff on the left. So this is for my Synergy 626. So basically it's a 600 size helicopter. So that means the blades are 600 millimeters long. So it's got a rotor diameter of about 1.3, 1.4 meters with the hub. So using the SysID mode that Leonard kindly developed and got in there, we were able to do these chirps in the pitch and the roll axes, and then be able to do an analysis afterwards to determine, you know, how much of this is due to what kind of time delay do we have in the system that's due to actuators. And you can see here we have a pitch of about 54 milliseconds and roll about 30 milliseconds. And then you know, now we can look at, hey, let's look at the pitch and flap regressives and see where they're at, pitch and roll flap regressives, and see where they're at. And so you can see on here, this is the top plot is the gain. So this is output to input, the ratio of output, flapping output over the input from the to the actuator. And so never mind what the actual value is in dB, but what's important to note here is kind of this hump out here. You see this hump in the pitch, and that's essentially indicating that there's an unstable mode, right, out there. And see, this roll has this hump here, this first one. These are both the flap regressive modes. And you can see here we have the pitch flap is at 3.5 hertz, and the roll flap is at 5.2 hertz. And you can see that the damping ratio, right, is just kind of says this is saying like it's 27% critically damped, where critical damping is like that it would approach at a asymptotic, a very well damped system. So this is just saying that, hey, it's fairly oscillatory. You'd probably have 5 or so overshoots before it hits steady state because of this. Whereas the roll has a little bit more damping, but still fairly lightly damped modes. And that's why it's really difficult for us to tune, because we're already fairly lightly damped. Now we add a little bit of P or D gain, and this basically starts to drive the rotor unstable. And then you have the lead lag regressive, which is sitting out here at 10 hertz, and you can see that out here at the right, which is the other one that you could, and so you can see the gain on the lead lag in the roll is actually still fairly got a lot of energy in it. So as far as the pitch and roll tuning philosophy, you know, I attribute a lot of your disturbance rejection and how well you can maintain that target response is how high you can tune your P and D gains. Because remember, those really provide that strong resistance to the deviations from the rotor deviating from the target response, or the aircraft deviating from the target response. And so it's really necessary, since we can't really tune those very high, we have to really rely more on the attitude feedback to provide stronger attitude or disturbance rejection, and to improve how well the aircraft follows the target response. And so that kind of lists there kind of my general flow of how I would tune the controller in order to achieve a good response. Generally starting with a feed forward to match the actual response to requested, and then doing your P and D gains to get as much of those in there as you can, and then setting your I gain to match your feed forward, and finally upping your attitude controller. Again, this attitude feedback is where you're getting most of your disturbance rejection, because you're really not getting a whole lot out of the P and D gains, because you're generally not going to be able to get them up very high. And then kind of the thing we've always talked about is this harmonic notch. We've been raving on the multi-copter side. They've been raving about the harmonic notch. I've been raving about the harmonic notch on the Heli side. Great piece of work by Andy and Leonard. Really thanks for their work on this. So it cleans up those vibrations, what I consider the vibrations. Real quick on that. So rotor speeds are kept constant for Helis, and typically the vibrations you see are multiples of the rotor speed. And so kind of like Leonard was talking about, hey, he looks to do the first harmonic, which is the rotor speed, the second one, which is the blade passage. So if you have a two-bladed rotor system, it's two times the rotor speed, and then we do 4 times the rotor speed, because that's essentially the next one that has a significant amount of energy. And you can see here, this is the pre-filtered signal, and you can see here this is your first mode, which is the rotor speed, your second, and then your fourth. And so afterwards, you can see you apply this notch filter along with you can actually raise your low pass filters to like 20 hertz now, and be able to take out the rest of this up here with that low pass filter, and then you can hit all these guys and not have to have your low pass filter so low that you're affecting and getting lots of time delay. And then what you're left with is essentially your rotor modes that are basically down below 20 hertz, really below 10 hertz. Big point here is that, hey, the harmonic notch is great, but it does not exclude the need to track and balance your rotors. You really still need to go out and understand how to track and balance your rotors and do it well. It certainly helps, but you know, you really want to make sure you have good track and balance. All right, 10 minutes left, getting on to improving the controller. Kind of three things I'm hitting on here: shaping functions and how they could be done to help provide a more realistic target for the aircraft, uh, accounting for delays in the system to help uh, align the command model with the aircraft response. And then lastly, this feed-forward derivative term, which is essentially help improve the vehicle response for axes that have kind of more of an acceleration command, which is mainly true for all the axes in a multi-rotor and basically the yaw axis for a helicopter. All right, real quick, control architecture. So most manned applications use what we call an explicit model following control law design. What I've turned with, when I talked with Leonard, I said, what we're using is more of kind of an implicit. And the difference is that with an explicit model following control law design, the designer knows the dynamics of their system. They basically spend a lot of time figuring out the dynamics of the plant, of the aircraft. And so then they inverse that so that they can then, you know, tell this inverse plant, hey, here's the response I want. Tell me what outputs I need to, or tell me what the controls I need to put into the system in order to get that response. And that's kind of what this is doing here, this inverse plant. And then the command model is basically, you know, you're the pilot. How do you want the aircraft to fly? You know, what do you want full stick to mean as far as roll rate or pitch rate? You know, it's basically it's defining how the response should be, and that's essentially what Leonard's doing with with the shaping functions, but they call it a command model. And so basically, you make the commands, it inverses it, tells it and it basically gives the outputs of what they should put into the controls, and then you get the aircraft response, and that comes back. And so no models are perfect. They're useful, but they're not perfect, as we like to say. So basically there's nonlinearities and things that can happen, disturbances as well. And so that's compared with the requested response, and then it's fed back in to help modify and make the aircraft achieve the desired response. And what they do is they add this equivalent time delay here in order to help better match the aircraft response. Because if you don't have this time delay, you may be, and there's lots of delays in this aircraft response, then you're going to be mismatching the requested response with the actual response of the aircraft. And so the big difference between manned applications and what we're doing here with ArduCopter is that we have one controller that we're trying to apply for thousands of different types of aircraft, helicopters and multi-rotors, different configurations. And here they're just worried about one, and they just basically define their dynamics for this aircraft, and they're able to kind of tune it a lot easier. So here's a you know, our design for the ArduCopter. We have our shaping functions. Then that gives a targeted rate that's modified by the attitude controller when it compares the target attitude to the actual attitude, and then it's given into the feed forward, or essentially given to the rate controller. Maybe I don't, Leonard, you probably can tell me how well I did this here, but basically the rate controller has both the feed forward and the PID, and that's basically provided into the aircraft, and you get your response. So again, the controller has no knowledge of the vehicle to determine the output for desired response. So it really depends on how well you tune. Like for multi-copters, you're just basically tuning the PIDs. And actually, Leonard's done a lot of work behind the scenes in the motors class to kind of linearize the response, get rid of the propeller effects and delays there. Whereas the helicopters, we have to use the feed forward to help us out a lot, and we have to tune that when we are tuning our aircraft to get the proper response. So like I was saying before, I'm I was looking at the shaping functions for ArduCopter. And for acro, what I found is that it's pretty much acceleration limited, but really there's no limit to jerk. Essentially, as soon as you say, hey, I need this requested rate, it goes up on that, that acceleration limit immediately, or goes to some acceleration immediately. There's really no turnover or essentially limited jerk response here. And so it's really difficult for an aircraft to follow that. And so you really have to dial down your acceleration. You know, the aircraft can actually probably do the acceleration. It just can't get to that acceleration instantly in some cases. So, you know, I'm proposing that we have kind of a rate shaping where I used a second order response, and I used an input rate time constant. You know, Leonard uses an input time constant for the stabilized mode. I'm proposing a rate time constant. And again, this is kind of the rise time of how fast it gets to that output rate. And then we have a damping ratio of like, you know, 0.8. So there's a little bit of an overshoot, but it helps get it up there faster and get on that rate. And then I applied, in order to kind of turn this up a little bit here and help it get up onto the acceleration without, not too quickly, I applied a first order lag to the jerk to provide a more gradual build of that initial acceleration. It seemed to work well. I couldn't really specify and move that jerk response around too much because I'd get some unexpected responses, especially when I got into kind of applying this to the attitude control. And so here's kind of the current versus the proposed for attitude shaping. So, you know, the current one is this square root shaping function. And so basically it comes up, here's this red here, and it achieves the attitude very nicely, but the rate is really jagged and very unrealistic for any really vehicle to follow that rate response. And so it makes it very difficult to follow that. And so what I'm proposing is we get a nice, essentially what I used is the existing attitude shaping function to determine the requested rate. And then my proposed rate shaping would then shape that rate to then get it there in a nice fashion, much nicer, realistic response for the aircraft. All right, time delay. I initially was desired to put the time delay in both rate and attitude feedback so that you could help look at the delays there and match them better for what's you know, what the actual response of the aircraft is to what the shaping function is requesting, because there are going to be some delays in the aircraft response. And so to kind of show here where I wanted to insert them, and I did some initial testing with this on some of my helicopters. And then I talked, and so kind of how that looks here is here's the response, here's the roll rate here, the attitude response here. And so you can see this is the requested, here is this in red, or the target response is in red, and then in black is the actual aircraft response. You can see there's quite a delay here in the rate. There's even a delay in the attitude, and you kind of overlay the rate delayed. And you can see if I delay the rate by 57 milliseconds, then it kind of nicely is overlaid by the actual response. And that would mean that I'd have lower deviations in the P feedback, and that would help reduce the oscillations and potentially reduce the overdriving of the response. And then I can also do that and kind of in the attitude. And here, there's a 30 millisecond delay in target attitude, which helped provide kind of a little better matching between the target and the actual aircraft response. So after talking with Leonard, we really it was decided that it would be more universally usable in the code to look at time delay just in the target attitude, because in most cases, kind of universally thinking multicopter and helicopter, right? Multicopters don't use feed forward, and really for this to work, you need to be able to apply that feed forward input, because that's the whole reason you're getting the aircraft going with the feed forward, so that you can kind of get the aircraft moving, and then you can compare its response to what you requested, and then modify that to then make it match more closely. And so really relies on the fact that you have this feed forward, and therefore kind of multicopters don't use this. So really it was better just to put it in the attitude controller loop rather than also into the rate controller. All right, last one I think I have here is talking about derivative feed forward. And generally, my intent for the derivative feed forward was to really give kind of we use it in the manned world, kind of in the derivative form, as kind of this washout filter. Effectively, you're trying to get if you have a really high inertia type aircraft where it's really tough to get the thing moving, you put a washout filter. You could use a D term to kind of initially give it a real kind of a goose and get that mass moving, and then you kind of wash out that input. And that's kind of what this derivative feed forward is going to act like, this lead filter. But also for axes that are more acceleration command, this would be useful for that as well. And so we started playing with that, and unfortunately I didn't implement it all that well, and we missed something. And so unfortunately Josh had a little accident there, and because we didn't account for my time delay, that was modified kind of how we restrained the yaw axis. But anyway, we're working through things, trying to further test this derivative feed forward and see look at the usefulness of it for helicopter and for multicopter. So in the future, just to wrap up, looking to do some automated handling of engine throttle for autonomous operations. We're basically really looking to kind of explore this whole idea of the helicopter. Once the motor started for internal combustion engine, then you're able to kind of bring the aircraft up all by itself. It can bring itself up to normal operating rotor speed, and then do the launch fully autonomous. So that part of this is going to require handling engine throttle as well for internal combustion engines. That helps with the warm up and the cool down, and other things. I want to look at doing better tuning instructions, and I'm really looking at auto tune. I know trying to incorporate an auto tune for Heli is way overdue, because it would really help our users get an initial tune and help them out a lot. There's I-term handling and limit handling. Leonard does a lot of this stuff inside multicopter, and I really need to look into the helicopter and see how we can be doing that better, especially for ground air transitions is really where this I-term handling is going to be necessary. And then limit handling is kind of the idea of, hey, you're pulling so much collective, what are you going to prioritize as far as control of the aircraft, that kind of limit handling. I already kind of talked about the reliable, fully autonomous flights from startup to shutdown. We got Matt working autonomous auto rotation, or at least like I call it assisted. And then finally, I'm gonna probably call on Tridge or Randy or Peter to kind of help me. Hey, look through the Trad Heli files, and oh gosh, I don't know if I want them to do this, but help me. Is there ways that I can improve code efficiency? So it's kind of some of those maintenance types things that we probably need to do with the Trad Heli files. All right, questions.
Mate. Well, I just wanted to say, can everybody tell why I enjoy having Bill's input so much on the code, and why it's been so useful working with Bill? with the Heli stuff, not just for the Heli stuff, but also the multi-rotor stuff. So yeah, thank you very much, Bill, for all your time and effort that you put in. It's really made, it's injected a fresh air into the whole control development. So yeah, sincere thank you.
Thank you, Leonard. Appreciate that.
Now the criticisms.
Bring it on.
But no, a few comments on the thing. Just so people put all this in perspective, one of the balancing acts we have to deal with as we're doing this is parameter bloat. So we've got to be very careful. There's a lot of background work that goes into choosing what the next parameter we're going to add in to make sure that it's actually worth the cost of that added parameter. And so it doesn't just come down to whether or not we can justify the parameter. It comes into whether or not we can actually support the users in using that parameter. So the delay values, for example, the attitude delay is an obvious thing that's easy to see and creates a direct overshoot on due to that chase and attitude. We close that down quite quickly, and so that's a delay that can be implemented quite safely in the attitude controller without worrying too much about, it's relatively forgiving for the users as well, and relatively easy to look at a log and actually see what it is. The rate delay requires more finesse from the user to put in, but it also needs to go into a different place. Currently that PID object incorporates both the feed forward path and the PID path. So if we put a delay in there, we would need to add it into the PID objects itself, which actually isn't overly difficult to do, but we need to understand what the requirements are and what the benefits are. So for example, do we need a delay, an overall system delay? Is that good enough with one parameter, or do we need 3 axes of delay for roll, pitch, and yaw? One of the other things that sits in my mind is, should we be adding functionality for a notch filter running inside of the PID loop at the 400 Hertz rates in order to deal with some of these problems that Heli in particular faces? Would that be a significant advantage for Heli if we had that at the PID level on a per axis basis, because each of those frequencies are different for each of the axes? And so we need to go. So one of the reasons why Bill's work so valuable is that there is a tendency for people to just say, "Oh, this made a big difference. Let's put it in." And it made a difference for me, without going through the rigor that Bill's been going through to actually really evaluate, the priority of each of these parameters. And then development, it's a long-term battle as opposed to a short-term one. And a lot of the Andy, for example, I spent a lot of time talking to Andy, sort of saying, look, we just got to be patient and slowly get this FFT stuff in. We can't, there's a whole heap of stuff that's going on that, aircraft are flying quite well at the moment. There's a whole heap of stuff that's going on that, although this is making a really big difference, we need to put it in one step at a time and work with the releases so that we can actually maintain, because it's only one small aspect of a much larger effort by a much larger group of people. So that's where Josh's help actually doing the, like going through hours of tuning to actually, you know, evaluate, give us another data point. You know, we've got Bill's Helis and we've got Josh's Heli, and, you know, my tuning approach versus Bill's tuning approach, and trying to see, trying to sort of rank what the next big step will be to make the biggest difference to heli tuning, and how we can actually, you know, creep these incremental changes in a way that doesn't add too much load to the larger development team, and also in a way that we can actually train up heli users on being able to use them. And that's where auto-tune could be this huge benefit to heli users, because just most heli users don't know how to even set their feed forward properly, because you really need, at the moment, you need to actually do a flight and then examine your log and then sort of work it out with some maths and a very clear understanding of the way the actual controllers work to actually calculate that. It's very hard to sort of just do it by eye. Yeah, on things, the acro, the acro is sort of, there's two sides of that. One of them is that there is potentially a real need on the ground for multi-rotors and helis on acro to sort of have this soft ground handling thing where, you know, the ghost moves on top of the actual when you're on the ground. At the same time, in the air, I think there's an inappropriate use of that actually, I suspect, and this is just my feeling here, because I haven't actually looked at logs and worked directly with one of those heli users that's got that feedback. But I suspect the feel that people notice when they actually enable that feature in the air is specifically because they're running higher accelerations than their helicopter is actually capable of with the tune that they've got, and that softness in the air is actually taking the edges off of a bad tune, and actually slowing things down and creating less overshoot for the pilot and making it feel nicer. Whereas if we can get auto tune running through and getting people's tune much tighter and actually using the input shaping correctly, I suspect they'll be able to get, you know, they'll be able to take those soft edges off using the attitude controller in the way it was intended when it was designed. So there's sort of two sides of that. One of it is perhaps there's a little corner there where with just multi-rotor acro that we should be supporting better and would actually enhance multi-rotor as well. And that's where the whole spool logic came in. We needed to support heli better and support, like there were some states during startup that were ignored in multi-rotor because we had this instantaneous startup. But for helis, it actually, it's really important. The bit that people sort of miss when they're looking at that and they're used to using small multi-rotors is those states are actually also really important for large multi-rotors as well. And so we've seen this big positive cross-pollination of trying to accommodate the needs of heli back down in the lower code, while at the same time, you know, although a lot of people aren't, it's not actually readily apparent, it's actually been really positive for a lot of aspects of multi-rotor as well. So working with Bill's been really beneficial, not just to heli, but also to the larger multi-rotor code. So yeah, that's sort of my little quick overview of those various things. So yeah, thank you very much, Bill.
Yeah, no, and I agree that we got to be careful about implementing some of these features and making sure that it's users can understand and use them effectively.
Yeah, I
Fantastic.
hope that Bill's talk, though, sort of went a long way to sort of showing people, you know, that we still do actually have a lot of, you know, a lot of advancements we can make at the control level. And, you know, but at the same time, the reason why we're not progressing quickly is because we do respect the parameter bloat problem, and we are trying to do our due diligence in minimizing those parameters as we go forward. So when we do suggest a new parameter, it is because we are seeing real performance improvements in the aircraft, and we believe it's actually important for the it will make a real difference for the quality of control of those aircraft moving forward.
All right, so thank you very much, Bill, and thanks, Leonard, for that, the perspective from the overall control point of view. Have we got any other questions for Bill? Anyone else from?
Yeah,
Yes.
Can I ask a question?
Yes, of course.
Bill, it's Matt.
Hey, Matt.
So with, are you seeing much uptake in some of the other types of rotor head, like teetering rotor heads and articulated rotor heads in the sort of ArduPilot community?
Probably. I mean, really, you mean like teetering rotor heads that don't have dampeners in them?
Yeah.
Yeah, not a whole lot from the smaller sizes. I would imagine if you got to a larger, Schweitzer 333 or something that's a bigger, 1,000-pound helicopter, if you're planning to use something like this, or maybe even 200 or 300 pound, they might have some rotor systems like that. But typically for the smaller helicopters, generally most of them use in some form or fashion a dampener in there that provides a stiffer rotor system.
Okay.
Any more questions from the floor? All right, I'd like to provide a big thank you to Bill.
There's a question, sorry, Rich, there's a question from Ken King.
Ken?
I think it's to Bill about if you have looked at asymmetric main blades, how do they affect the control systems?
I have not, I don't have any discrete data on that. I would imagine from what I know about manned helicopters, certainly asymmetric blades where you're saying like a cambered blade that provides, they're more of like a performance thing, right? You're gonna give yourself better performance, but as from a handling qualities and a control aspect, I don't think that they would certainly, obviously drag, and there's some things that are going to improve. I don't know that you'd see that big of a change or a difference from a control standpoint. That's just my thoughts.
All right, thank you very much. So a big round of applause for Bill. Say thank you very much for a fantastic presentation, and also for all of your effort that's been put into Heli. It's been absolutely brilliant. Thank you.
Thank you. Thank you.
Thank you.